So as I was mentioning, we're going to start tonight by drawing the alpha and beta anomers for a ketohexose. And essentially the steps that we talked about last time that you saw in the notes and had a chance to practice in the homework as well, the steps are not going to change, but what we're going to draw is going to be a little bit different, starting with a ketohexose rather than an aldohexose. So the first thing I would do is I would number the carbons starting from the top, 1, 2, 3, 4, 5, and 6. So as we know, our first step is to take the Fisher projection and turn it 90 degrees clockwise and redraw it horizontally from right to left. And as we discussed, the main purpose of this step is to really get the correct translation of the OH groups on the chiral carbons in the Fisher projection, left and right, to those carbons in the Howard structure in terms of going up and down. Because as we talked about, essentially, if you have an OH on a chiral carbon in a Fisher projection pointing to the left, in the Howard structure, that OH group should be pointing up. And if you have an OH going to the right on a chiral carbon in a Fisher projection, in a Howard structure, that OH should be going down. And there's one exception to that, as we talked about, that's the last chiral carbon, because that's the one that the OH oxygen is going to be used to form the ring. We'll get back into that in a moment. But other than that, that's the correct translation. So essentially, the main carbons of interest here, when we turn it 90 degrees clockwise, are carbons 3, 4, and 5. Because for a ketohexose, carbon 2 is not chiral. Carbon 2 is the C double bond O carbon, which makes it achiral or not chiral. So for carbons 3 and 4, the OHs are pointing to the left. After I turn it, the OHs on those carbons are going to be pointing up, and the hydrogens are going to be pointing down. And then for carbon 5, the OH is pointing to the right. After I turn it, the OH is going to be pointing in what direction? Down, and H up. So that would complete step 1. Okay. Step 2. First off, let's figure out the ring size. So we're going to start with the C double bond O carbon. We're going to include all the chiral carbons after that, which are 3, 4, and 5. And we're going to include the oxygen of the OH group on the last chiral carbon. So in this particular case, how many atoms is that total? It's 1, 2, 3, 4, and 5. So in this case, instead of drawing a hexagon, we're going to actually draw a pentagon for our ring structure. Now, just like we did for the six atom ring, we're going to start with the C double bond O carbon furthest to the right. And then from there, we're going to go clockwise. Okay, so we have carbon 2, carbon 3, carbon 4, carbon 5. Now, for carbons 3 and 4, I want to fill in the OHs and the Hs like I have in my horizontal picture. So for carbons 3 and 4, you're going to have OH up and you're going to have H down. Now, carbon 5. We talked about in the notes and last week that for the last chiral carbon, carbon 5, rotation takes place before the ring forms in order to get the OH group on that carbon in proper position for ring formation. And I mentioned that that rotation is really consistent from example to example. And this example is no different. So carbon number 6 is going up. The hydrogen on carbon 5 is going down. And the only real difference is that instead of the OH going directly to the right, in these cases, the OH is going to be going to the right, but diagonally up. Now, I'm not going to put the hydrogen on there because if I understand what's going to happen, I know that the hydrogen on that oxygen, when I form the ring, is going to come off. So now let's form the ring. So we take the hydrogen off of the last chiral carbon. So this hydrogen off of carbon of the oxygen on carbon 5 is gone. And that oxygen is going to form a bond to the C double bond O carbon, which is carbon 2. Now, two things. First off, carbon 2 is still going to be connected to carbon 1. We have to fill that in. And the other aspect is what happens to the C double bond O group. The double bond between the carbon and the oxygen becomes a single bond, and that O essentially becomes what? OH. So one way to put that in would be to put the OH going in the downwards direction and carbon number 1 in the upwards direction. Now, in this case, because I've chosen to put the OH on carbon 2, which is a new chiral carbon, in the downwards direction, what anomer of this ketohexose would I have made? This would be the alpha anomer. And that's because the OH on that new chiral carbon is going in the downwards direction. So that would be the alpha anomer. Now, for the beta anomer, if I've done everything right, I'm essentially going to retrace my entire alpha structure, except for what's going on carbon 2. Because the other possibility is when the oxygen on carbon 5 bonds to carbon 2, there is also a possibility that when you get the double bond between the carbon and the oxygen on 2 becoming a single bond and that O becoming OH, it is like also possible that that OH could be pointing up. And we know that these would be distinct structures because you cannot rotate around the carbons of a ring. And then, of course, the other thing attached to carbon 2 is still carbon number 1. But in this particular case, because the OH on carbon number 2 is going in the upwards direction, our new chiral carbon, what anomer of this ketohexose would I have made here? This would be the beta anomer. And again, notice that it's exactly the same as the alpha anomer, except what's going on at the former C double bond O carbon. Because the OH that forms on that carbon has equal odds of going up or down, and you can't rotate from one to the other. All right. So one of the things we're definitely going to ask you to be able to do is to take an aldohexose or a ketohexose and draw the alpha and beta atoms.
Okay, if we did it as alpha or beta, it's like an equal toss up, you said?
Yeah, and probably I would ask you to draw both.
Okay.
Yeah, so you would definitely get both. The relative percentages would probably be close to 50-50.
Okay. Thank you.
Of course. Other questions? Okay. So one of the other important aspects in terms of monosaccharides is their oxidation. And really not only oxidation of monosaccharides, but a broader discussion of oxidation of carbohydrates in general. It turns out that monosaccharides, and really all of them, undergo oxidation to have the C double bond O group converted into a carboxyl group. And we know your carboxyl groups are the main component in what types of compounds. Your carboxyl groups are the main component in carboxylic acids. Now, the reason why this should be a little bit surprising is because if you think about ketoses, like fructose, when you go back and think about our discussions in chapter 12 about oxidation of alcohols, aldehydes, and ketones, we talked about the fact that for ketones basically do not undergo oxidation. But surprisingly, in a sense, your ketoses, your monosaccharides that are ketoses actually undergo oxidation as well, because they actually go structural rearrangement to have the ketone group converted into an aldehyde group. Now, we're not going to ask you to draw the products of the ketoses and oxidation, but we will ask you, or you need to be able to, draw the product of an aldose and oxidation. So, and again, it doesn't really matter what the chain length basically is. But basically, if you come across an aldose and oxidation, we have to remember back to our discussions in chapter 12, how to convert that aldehyde into a carboxylic acid. And essentially, you take off the hydrogen of the aldehyde group and you replace it with OH. And upon doing so, that would give you a carboxylic acid. Okay. So it turns out that disaccharides may or may not undergo oxidation. As far as polysaccharides go, I don't really think that polysaccharides undergo oxidation, but disaccharides may or may not undergo oxidation. And it turns out that carbohydrates that undergo oxidation are known as reducing sugars. So the thing to remember about reducing sugars is that a carbohydrate that's a reducing sugar doesn't undergo reduction. A carbohydrate that's a reducing sugar actually undergoes oxidation. But what it's reacting with to cause it to undergo oxidation, that other substance is being reduced. And you had a chance to look at that in the carbohydrate lab when you used Benedict's reagent and also with Barfour's reagent as well. You know, especially with Benedict's reagent, when Benedict's reagent causes a carbohydrate to undergo oxidation, the copper in the Benedict's reagent is reduced. And it's a nice way of seeing the carbohydrate undergo oxidation because the copper changes from blue to red. Otherwise, you can't tell at all that the carbohydrate is undergoing oxidation. Now, most of the time, carbohydrates exist in ring structures with no C double bond O group present. So, how can we tell from a Haworth structure, which of course are your ring structures, that a carbohydrate is a reducing sugar? And what we do is we look for what is known as a free OH group on an anomeric carbon. So, what does this look like? So first off, whether it's a 5-atom ring or a 6-atom ring, the anomeric carbon is always the carbon directly to the right of the oxygen. Whether it's a 5-atom ring or a 6-atom ring, the anomeric carbon is always the carbon to the right of the oxygen. what does a free OH look like? Well, a free OH, whether it's up or down, a free OH essentially just looks like OH. What makes it free? What makes it free is that that oxygen is not involved in a linkage to another monosaccharide. And we're going to talk about disaccharides in a few minutes. But when that OH group is not there, that oxygen is involved in a linkage to another monosaccharide. So that hydrogen is not there. So basically, you don't have OH. So if you go back to the example that we did with this ketohexose, the way I would know it's a reducing sugar is whether you look at the alpha or the beta form. If we look at the alpha form, where's the anomeric carbon? The anomeric carbon is carbon number 2. In the ring structure, does that carbon have a free OH? And the answer is yes. Where is that free OH group? It's right here. And even if you look at the beta form, the anomeric carbon's the same. Where's the free OH? It's right here. So even though this is a ketohexose, I would expect this compound to be a reducing sugar. And, because carbohydrates, monosaccharides, disaccharides, polysaccharides mostly exist in their ring forms, we have to be able to tell from a ring structure whether the carbohydrate is going to be a reducing sugar or not. And that's how we're able to tell. Okay. All right. So the last part of the chapter that we covered deals with disaccharides. And essentially, what you have in your disaccharides are 2 monosaccharides linked together by what is known as a glycoside bond, which for carbohydrates is essentially an ether group. And hopefully by now you're comfortable in terms of knowing what ethers are. Of course, for an ether, you have an oxygen, and that oxygen is singly bonded to 2 carbon groups. And the 2 carbon groups may be the same, or they may be different. So I don't expect you to memorize the structures of the disaccharides. So I'm not going to say draw lactose or draw maltose or draw sucrose or any other ones, which I don't even think the textbook lists anymore, but I'm not going to ask you to be able to draw them. But what you need to be able to do is you need to be able to tell or be able to do three things. First, you need to be able to name the linkage. Okay. So there were 3 linkages that we came across. So how do you name a linkage? You give the carbon numbers involved. Give the carbon numbers involved and alpha and or beta if the linkage involves an anomeric carbon or anomeric carbons. So with that being said, there were 3 linkages that we came across. The first one was an alpha 1,4 glycoside bond, or an alpha 1,4 glycoside linkage, however you want to referred to it as. So what did that look like? That looked like the following. So one of the things that we talked about in the notes is that, you know, for the 6-atom ring and the 5-atom ring, you sort of really have to be able to number the carbons correctly. For a 6-atom ring, the carbon directly to the right of the oxygen is carbon 1. And then from there, of course, you would go clockwise around the ring. So 1, 2, 3, 4, 5, and then 6. So if you take a look here, the linkage involves carbon number 1 of the first monosaccharide, whatever it is, and carbon 4 of the second monosaccharide, whatever it is. And carbon number 1 for the first monosaccharide is the anomeric carbon. Carbon number 4 for the other monosaccharide is not the anomeric carbon. So for carbon 1, we have to give the direction. This is how it's done. We have to give the direction the linkage is going as part of the name of the linkage. So off of carbon 1, the linkage is going in a downwards direction. And what do we call downwards in terms of carbohydrates and Howard structures? We call that alpha, especially for the fact that it's coming off an anomeric carbon. So this linkage would be what is known as an alpha 1,4 glycoside bond or glycoside linkage. So that's the first one that we came across. The second one we came across was a beta 1,4 glycoside bond. Now, what does that look like? That looks like the following. Sorry, I knew I sketched it wrong. All right, I apologize. I'm just going to have to erase quick because I ran out of space on my writing board. Better. And so again, we'll number the carbons as well. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So again, the linkage here involves carbon number 1 of the first monosaccharide and carbon number 4 of the second monosaccharide. Carbon number 1 is once again the anomeric carbon for the first monosaccharide. Carbon 4 is not the anomeric carbon for the second monosaccharide. So off of carbon number 1, we have to give the direction the linkage is going using the correct terminology of alpha or beta. In this example, the linkage is going up. And off of the anomeric carbon, what do we call that? We call that beta. So this would be a beta 1,4 glycoside bond. And just like the alpha 1,4, you have COC. What type of functional group is that? That is your ether functional group. Okay. So that was the second linkage. And then the third linkage is an alpha beta 1, 2 glycoside bond. Now, what does that look like? That looks like the following. Thank you. Okay. So here's what this particular linkage looks like. Let's number the carbons. So for the top one, 6 atom ring, we have 1, 2, 3, 4, 5, and 6. For the bottom one, now the one to the right of, so keep in mind now, since for the 5 atom ring, the carbon to the right of the oxygen is not 1, the carbon to the right of the oxygen is 2. 1 would be at the bottom here, and then around the ring, you'd have 3, 4, and 5, and then 6 would be going to the top. Off of carbon 1, the linkage is going down. Off of carbon 2, the linkage is going up. 2 carbon numbers involved are 1 and 2. Carbon 1 is the anomeric carbon for the top monosaccharide. Carbon 2 is the anomeric carbon for the bottom monosaccharide. Remember, the anomeric carbon is directly to the right of the oxygen. So here, the linkage involves both anomeric carbons. So we have to give the direction off of both. Off of carbon 1 down, alpha. Carbon off of carbon 2, it's going up, beta. So that's where the alpha, beta, 1, 2 comes from. The numbers are 1 and 2. 1, that's why the alpha is first and the beta is second. So it's an alpha, beta, 1, 2 glycoside bond. And the reason why that there's alpha and beta there both is because the linkage involves both anomeric carbons that are present. Essentially, if you think about disaccharides, disaccharides have 2 anomeric carbons. Basically, each monosaccharide in a carbohydrate provides an anomeric carbon. All right. So there are other linkages as well, but these really are the 3 linkages that I expect you to be able to recognize: alpha 1, 4, beta 1, 4, and alpha beta 1, 2. Okay. Second, tell if the disaccharide is an alpha anomer, a beta anomer, or neither one. And I'm going to mention the third thing as well, because as you saw in the notes, these 2 things are actually intertwined. Tell if the disaccharide is a reducing sugar or not. And these 2 things are intertwined because to answer them, we look for the same thing. So we look for the same thing for both. And it's the following. We look for a free OH group on an anomeric carbon. Because if you have one, its direction will tell you whether the disaccharide is an alpha anomer or a beta anomer. If it's going downwards, the disaccharide is an alpha anomer. If it's going upwards, the disaccharide is a beta anomer. But if you don't have a free OH on an anomeric carbon, then then you don't have alpha and beta anomers. That disaccharide only exists in one version. And if you have a free OH, independent of whether it's going up or down, it also tells you that the disaccharide is a reducing sugar. If you don't have a free OH, then the disaccharide is not going to be a reducing sugar. So let me just show you sort of a sketch. Put that other CH2OH in the wrong place. There we go. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this particular disaccharide, whatever else is filled in here, really wouldn't make much of a difference in terms of answering questions 2 and 3. This particular disaccharide has 2 anomeric carbons. Here's the first. That would be the anomeric carbon for the first monosaccharide. There's the second. That would be the anomeric carbon for the second monosaccharide. For the first monosaccharide, do you have a free OH on an anomeric carbon? No. The OH, the oxygen is involved in the linkage to the other monosaccharide. It doesn't exist as OH, it's involved in the ether group. So you don't have a free OH. But what about this other anomeric carbon? Does that have a free OH group? And the answer is yes. That anomeric carbon has an OH attached to it. Now, because that OH is going up, that tells us that this disaccharide is a beta anomer. Not so much worried about the name of it, because I'm not going to ask you what the name of it is, but you should be able to tell that this disaccharide is a beta anomer. Keep in mind that if you were to name the linkage here, the linkage is actually alpha 1,4. So one of the things sometimes students get confused with is that they think that the linkage, and to tell if the disaccharide alpha or beta, that it has to be the same. No, it doesn't. It could be the same. You could have an alpha 1,4 linkage and an alpha anomer, or like in this case, you could have an alpha 1,4 linkage and a beta anomer. That's absolutely possible. So you sort of have to separate the two. And then the other aspect of it is that once we find that free OH, it would also tell us that this disaccharide is a reducing sugar. It would also tell us that as well. So once I find that free OH, you should be able to tell that this disaccharide is a beta anomer and that this disaccharide is also a reducing sugar. So again, you don't have to be able to draw the disaccharides, but if we give you the structure of an actual disaccharide, those are the 3 things that I would expect you to be able to do. All right. Any questions about that? All right, so that was actually most of what I had in terms of carbohydrates. Let me go back a little bit. And again, if anybody has any questions about anything in general, you can feel free to jump in. Let me just go back and talk a little bit more. So in chapter 12, in our office hour sessions, we spent some time talking about alcohols, excuse me, aldehydes and ketones and their solubility in water. And I didn't get a chance in chapter 14 to go through that because I wanted to really spend time going over the reactions with you. But now that we have some time this evening, I want to talk a little bit about carboxylic acids and amines and their solubility in water. So let's start. Well, first off, as I was beginning to write, what is the key question that we have to ask ourselves to really determine whether a small version of a type of organic compound is going to be soluble in water? If it can do what? If it can hydrogen bond. In water. That's going to be the key question. Because if the answer is yes, then small versions of that type of compound will be soluble in water. So when we talked about alcohols, we talked about the fact that alcohols with 1 to 4 carbons are very soluble in water because each alcohol molecule could hydrogen bond with 2 water molecules. When we talked about aldehydes and ketones and their solubility in water, we talked about aldehydes and ketones are soluble in water because those that have 1 to 4 carbons, each of those molecules could hydrogen bond with 1 water molecule. What about carboxylic acids? Well, carboxylic acids with 1 to 4 carbons are also very soluble in water because each carboxylic acid molecule can hydrogen bond with 3 water molecules. So, in fact, if you think about it, what's really true is that as compared to even alcohols, carboxylic acids would even be more soluble than alcohols are because each carboxylic acid molecule can hydrogen bond with 3 water molecules. So let's go over why that is. So in the notes, when we talked about a carboxyl group, we talked about that a carboxyl group is amongst the most polar organic functional groups because essentially all 4 atoms of a carboxyl group have charge associated with them. We talked about how the C double bond O oxygen has a partial negative charge. The carbon has a partial positive charge there, not too important for this discussion. The OH oxygen also has a partial negative charge, and the hydrogen on that oxygen has a partial positive charge. The C double bond O discussion stemmed from our discussion of aldehydes and ketones, and the OH portion stemmed from our discussion of alcohols. So each of those oxygens with the partial negative charge are going to be attracted to what part of water molecules? Hydrogen, because the hydrogens in water have what charge? Partial positive. So here and here. And then the OH hydrogen would be attracted to what part of a water molecule? Oxygen, because the oxygen of water has what charge? Partial negative. Each one of these forces of attraction are examples of hydrogen bonding. Keep in mind, this is very important. Even though there are other hydrogens in this carboxylic acid, remember we talked about the fact that a carbon to hydrogen bond is a nonpolar covalent bond. And atoms in a nonpolar covalent bond are technically neutral. So the hydrogens on this carbon have no charge associated with them. And remember, hydrogens on carbons are never involved in hydrogen bonding because they are technically neutral. So keep that in mind. And then what we also talked about, just to remind ourselves, is that just like with alcohols, aldehydes, and ketones, For carboxylic acids, as the number of carbons in the compound increases, the solubility in water decreases, because again, the more and more carbons that are present, the more and more difficult it becomes for water molecules to get to where they need to for hydrogen bonding to occur. So again, we're not going to expect you to know exact cutoffs. We sort of have this 1 to 4 carbon rule. But again, if I gave you a carboxylic acid that has 9, 10 carbons, you should be able to tell me that that carboxylic acid would be insoluble in water. Okay. Let's talk about amines and their solubility in water. So, like OH, NH is a polar covalent bond. Nitrogen is more electronegative than hydrogen. So the electrons in that bond are going to be shifted towards the nitrogen. So the nitrogen has a partial negative charge, and the hydrogen has a partial positive charge. So your primary and your secondary amines with 1 to 4 carbons are considered soluble in water because each can hydrogen bond with multiple water molecules. Now, we're not going to go into the reasons why they wouldn't be considered very soluble in water if they can hydrogen bond with multiple water molecules, but the general idea is that they are considered soluble in water because they can hydrogen bond with multiple water molecules. So, for example, if we had something like this, where you had, ethylamine, water molecules would essentially be attracted to it as such. So the nitrogen in the amine would have a partial negative charge. The 2 hydrogens on the nitrogen would have partial positive charges. Each of those hydrogens on the nitrogen are going to be attracted to a water molecule. And the nitrogen is going to be attracted to a hydrogen of another water molecule. And again, all of those would be examples of what? All of those would be examples of hydrogen bonding. Now, it also turns out, or the textbook says, that your tertiary amines, and again, my expectation is, 1 to 4 carbons, but really tertiary amines would have to start with 3 carbons. I would say at best, and this is really probably pushing it, are slightly soluble in water. And the argument that they make, which I understand a little bit, is that they still consider the nitrogen to have a partial negative charge, even when there's no hydrogens attached to it and there's carbons attached to it. So what they talk about is that they talk about the nitrogen being able to hydrogen bond with a hydrogen of water. I don't know. I almost think they're almost insoluble in water. I mean, if they show some solubility in water, it's going to be very, very slight. So if I was going to ask you about amines, I probably would stay away from tertiary ones because I would probably make the argument that they're all insoluble in water. I could be wrong, but I would make the argument that they're insoluble in water. But your primary and secondary ones with 1 to 4 carbons, they do tend to be soluble in water because they can hydrogen bond with multiple water molecules. All right, so that was one thing I wanted to also discuss this evening. All right, mention a couple other things. A couple naming things. in chapter 14 that we didn't get a chance to discuss that I think um, might be a little bit difficult. I want to just mention them. So what if I said give the name of this compound here? It's an amine because the nitrogen has two carbon groups attached to it. One of them is, well, let's just say it this way. It has two carbon groups attached to it. But in terms of how we normally name amines, we give the branch names of the carbon groups attached to the nitrogen, followed by the word amine. And we use a prefix of di or tri if the carbon groups are the same. Now, the issue with doing that here is that in the textbook, we don't talk about what we call benzene ring as a branch. You might know what it is if you looked at outside sources, but this version of the textbook doesn't talk about what the branch name of a benzene ring is. So what the textbook talks about is that instead of calling or giving this compound a common name like something amine, in a sense, what they say here is use a parent name of aniline. Because remember, for aniline, you have a benzene ring attached to an NH2. Now, the difference here is that one of those hydrogens on the nitrogen is replaced by a carbon group. Now, if we call this compound aniline, the ring carbon that has the nitrogen attached to it, that carbon would be carbon number 1. And then you would number the carbons of the ring from there. But the issue is there's nothing else attached to the ring. This carbon group is attached to the nitrogen. So first off, what's the name of that carbon group as a branch? Well, that carbon group as a branch is what is known as propyl. CH2, CH2, CH3 as a branch is what is known as propyl. And how do we indicate in the name of this amine that that carbon group is attached to the nitrogen? We give it a location of N. So when the person sees this name, they know that you have a benzene ring with a nitrogen attached, but instead of having NH2, because it's N-propyl, one of those hydrogens is replaced by a propyl group. Could you have two carbon groups on the nitrogen? Yeah. Each of them would be at a location of N, even if it was the same carbon group. So like, could you have something like N dipropyl aniline? Absolutely. Remember, every branch has to have a location in the name, even if it's the same branch on the same carbon, or in these examples, the same branch on the same nitrogen. Now, could you have branches on the nitrogen and the benzene ring? Yes. I will not ask you about those. And I don't think the textbook asked you about any of those either. So you don't have to worry about those examples. Here's another one that sort of fits into this discussion of N. So this type of compound is an amide. We know it's an amide because the C double bond O carbon is connected to a nitrogen. And that defines an amide. We talked about the fact that for your secondary and tertiary amides, and of course, what type of amide is this? This is a secondary amide because the nitrogen has a hydrogen. Again, besides the bond to the C double bond O carbon, the nitrogen has a hydrogen and a carbon group attached to it. Primary amides, the nitrogen has two hydrogens attached to it. Secondary amides, the nitrogen has a hydrogen and a carbon group attached to it. Tertiary amides, the nitrogen has two carbon groups attached to it. So we talked about the fact to come up with the parent name, pretend that you're dealing with a primary amide. So then how do we go back and name primary amides? We pretend that we have a carboxylic acid. So in other words, instead of having NH here or NH2, we pretend that we would have this, CH3, CH2, CH2, C double bond O, OH. So that carboxylic acid would be known as butanoic acid. Take out the OIC, take out the acid. So the parent name for this amide would be butanamide. Now, there's a carbon group on the nitrogen. Again, in this case, that carbon group by its branch name is what is known as propyl. And how do we indicate that that carbon group is not on the nitrogen and not in the carboxylic acid portion of the amide? Because if we were going to number the carbons here, just to show you, the C double bond O carbon would be 1, and then I would number the rest of the carbons in the carboxylic acid portion. How do we indicate that this carbon group is attached to the nitrogen and not to the carboxylic acid portion? We give it a location of N. So this particular amide would be known as N-propyl butanamide. N-propyl butanamide. Okay. Let's look at one more example in that realm. So how would we name this compound here? So again, we'd want to pretend that the carbon groups are not on the nitrogen, which would bring us back to a primary amide. And then for the primary amide, we'd want to be able to go back and go from the corresponding carboxylic acid. The corresponding carboxylic acid here would have the benzene ring with a C double bond O OH attached to it. This carboxylic acid is what is known as benzoic acid. Take out the OIC, take out the acid, and the parent name for the amide would be benzamide. Again, carbon number 1 would be the ring carbon that the C double bond O group is attached to. But the carbon groups here are attached to the nitrogen. Both carbon groups are the same, they're both ethyls. So of course that would give us diethyl. And then how do we indicate that both of these ethyl groups are attached to the nitrogen? We would have N, N diethyl benzamide. So N, N diethyl benzamide would be the name here. Benzoic acid was one other name that we came across. Benzene ring with a carboxyl group attached to it. The ring carbon with the carboxyl group is carbon number 1. Also want to mention, just again, benzaldehyde. Benzene ring with the aldehyde group attached to it. And the ring carbon there would be carbon number 1. The ring carbon there would be carbon number 1. Let's see. What else? Anybody, any questions from any of you? Okay. Let's see, what else? Anything specific? Go back to monosaccharides for a second. We talked about oxidation. It also turns out that for monosaccharides, they can undergo reduction as well. Now, as I talked about with aldehydes and ketones, I wasn't really happy with the fact that for aldehydes and ketones, the textbook uses hydrogen and a catalyst, because as I talked about, most aldehydes and ketones don't undergo reduction with hydrogen and a catalyst. You can use something like sodium borohydride, NaBH4, which was what I expect you to be familiar with. Now for monosaccharides, I'm going to let the H2 sort of I'm going to be okay with the H2. So when you see a monosaccharide with H2, you have to think reduction. And what you should remember is your aldehyde and ketone reduction. So what did we talk about for aldehydes and ketones and their reduction? The double bond between the carbon and the oxygen becomes a single bond. And then you add two hydrogens, one to the oxygen, the other to the oxygen-bearing carbon. And that's it. After that, for this monosaccharide, everything else that was there would remain exactly the same. So I'm not as objectionable to using hydrogen here for either the reduction of the C double bond O group in an aldose or a ketose. We'll just let it be. But what you have to recall to yourself is that this reduction and how to draw the product is exactly the same as what we talked about for aldehydes and ketones and their reduction. So keep that in mind as well. Okay. Just running through list of stuff in my head. We did all the reactions. We did basically everything in carbohydrates. Did everything in chapter 12. All right, so exam Tuesday. Same format as the first exam, part multiple choice, part short answer. The reactions are going to be a big component. There's a lot of them. I really hope you started to, sort of get them into memory. Again, you don't have to memorize the monosaccharide. You don't have to memorize any carbohydrates. Anything you're expected to do, like draw the enantiomer, or draw the alpha beta anomers, or identify the parts of the disaccharide, you'd be given the structures and such like that. Your chapter 13 homework is graded. I'm going to try to get that back to you either later tonight or sometime tomorrow so you could have that to study from. And then, of course, don't forget to email me to select whether you want to take the exam during the morning session or the evening session. And if you have a conflict, like the first exam, please send me an email to remind me of that as well. And we'll probably go with the same time as you did for the first exam. All right. Any questions for me before we say goodnight? Okay. All right. So good luck studying. If you need anything, feel free to email me and I'll try to get back to you as quickly as possible. Next week, we'll jump right back into chapter 15, dealing with lipids. All right. All right. Stay well, everybody. Have a good night.
Thank you.
Have a good weekend.
Thank you guys. Have a good weekend.
Take care. Stay well.